The Bronx Zoo, though, can be a bit of a maze, which is a great segue to today's discussion of mazes. I got there eventually. Okay, so now that that is completely done, we are working on your new assignment, which is mazes. Now, this is one of the few bespoke assignments I've come up with that I think that I'm actually proud of. So in this assignment, which is your maze assignment, this goes over stacks and queues, but primarily stacks. Now, you do not have to implement stacks, or you don't have to write a stack or a queue. You get to use what's available inside of Java. Now, there is something that I have learned in the process of my very long period of writing my data structures textbook that I want to bring up, okay? Because it's not something I actually talk about in the videos, because I didn't know about it when I was talking about videos, and I've been busy trying to write this textbook over a long period, and I haven't touched it in apparently 8 months. Wow, okay. It's been a while, 7 months, so been busy, very busy. Okay, so let me go ahead and open up this PDF here to tell you about it, okay? So this is something, and you can, I have it linked in the Discord. Oh, do I not have it? Oh, okay, this part isn't compiled with all of it, I don't think. Yeah, I didn't compile it with all of it. That's part of the issue with working with LaTeX, is that occasionally you work and, do I not? I don't have tech. Oh, right, because I recently reformatted this guy. Okay, give me a second. Sorry. Restore previous session. History, restore previous session. We're going to go and just simply look at the source code, so as opposed to me going and giving you a nice looking PDF. But you can deal with it. All right. So raw. Right. So we're going to be learning how to use the stack in the in this class. However, in actual production, you should not use the stack or queue. Okay, that's what I wanted to get at. What I'm teaching you here with the stack and the queue is all great. It's all pedagogical. Everything you learn here will be usable. But in terms of actually using stuff in production, the stack uses the vector class, which is much older. But anyway, if you are going to use a stack in production, you want to use something called a deck, which is a double-ended queue. And the queue, and that's in my queue chapter. Where is queue? There it is, queues.txt. So the queue, the double-ended queue means it just it adds and removes at the end of the data structure. Kind of sounds like a double-ended linked list, right? But the idea here is you can use the deck as a stack. It's actually the recommended way to do so according to the Java documents, because it is just much more modern and efficient. And it is very easy to kind of just simply use what the code as a guide. But if you're using it in production and if you're going for interviews, you might actually, wow the person giving you the interview by knowing about the deck as opposed to using a stack or queue, right? Saying, okay, we can solve this with the stack, and because we're using Java, I'm going to use the deck. For Python, you're going to be using the list no matter what. So if you and as far as other languages, they probably use a deck as well, but you'd want to simply that's just something to ask. There's also a deck in Python to also use and also wow your interviewers with, so just keep that in mind. Okay, so that's all I have to say about actual production. But for right now, using stack and queue is pretty good. So I changed this, but I never uploaded the change with where I fixed the spelling error. Okay, so what we're going to be doing is using basically a basic graphic API that you saw earlier to do this problem. You get 3 classes, and I believe I gave you a description of all those classes, a video that goes over this. But just to be clear, the only thing you really should, there's only really a few things you should be modifying. Okay? Let me open up Geany because I don't want any AI kind of thing to not mess with my code or read my code. None of that paranoid stuff. I just don't want it to distract me with any kind of suggestions right now. That's completely unnecessary on our end. Okay. Sorry. So the only thing you really should edit here is in Maze. You want to edit this, and this line. This and this line can be edited. You don't need to until you're ready, though. This changes the size of the maze or the physical size of the screen, but you can do that by dragging anyway, so whatever. And this changes how big your actual maze is. Okay? Can't run it from here, that's fine. Cell, I've seen students... I had not seen students edit this until students started working with AI. Don't edit this code. This is going to be a good indication that you're working with AI if I start seeing this edited. Every cell, the way Maze works is that it's a bunch of squares. Every square has a north, south, east, or west wall. And if it's true, it has a wall. False, it does not. Your north wall is somebody else's west wall. Sorry, north wall, someone else's south wall, not west. Jeez. Compile. Build. Compile. And then... And this is what we get when we run it. Right? So I'm going to go ahead and compile this as a 10 by 10 maze. This is a very, very basic editor I use when I'm working in Python because I don't want something that looks like a flight control deck when I'm working with beginners. So over here we have my randomly generated maze. Now my randomly generated maze algorithm is very simple. It says no walls here on the first row, no walls here on the first column, so that there's always going to be a solution. And then for any other square, what we're going to do is we are going to flip a coin. And if it's heads, remove north-south, and if it's tails, remove your east-west wall. Make sense? So just notice how, and as a result, it creates a zigzag pattern. It's not a particularly clever maze. It's just very guaranteed that it's going to have a solution and very easy for me to implement, okay, and didn't require me to do anything that would possibly give you an answer on how to solve your problem. So where do you actually solve the problem? It is this, solve maze, okay? And you solve a maze using a stack to keep track of where you have been. Sorry, where your current path is, okay? And you keep track of like the solution and show that to the user by changing the color of the cell that you're currently at or where you'd previously been. You do that with the set background over here, right? You can see that in my code that I use set background to change the color. Set color dot, and then you can use any kind of common color name to change the color of it, right? I typically recommend blue, coloring in blue for whatever your solution is. I also provide you with this handy dandy method over here called visited, which lets you know, have I been to this particular square at this particular row column? Given a row column, it will get that cell from the, it will get that cell from the array that holds our maze. It'll get the color of that cell, and then what it will do is it will say if it's white or if it's red. Why red? The goal is colored red. Okay? If it's white or red, then it's a square we haven't visited yet. And so we'll return false. Any other color is usable to you as a color to mark that you've been there. I typically use gray for squares I've had to backtrack out of, and then blue for any square that's on my current path. Okay? So let's talk about how you solve mazes, because I haven't really talked about that, and I kind of got ahead as to where we are. So mazes are particularly fun. I love doing this. I prefer doing this in fall because we get to talk about hedge mazes around this point because it's time for Halloween, and that's when all the corn mazes and hedge mazes start up. But mazes, there are various strategies for solving mazes and generating mazes. Mazes are actually amazing practice for programming if you want, and there's different maze generating strategies. And you can do one of them for extra credit. But long story short, right, we have a couple of different ways to solve mazes. The first is the right-hand rule. And it's not the one where in engineering where you use your fingers to kind of say, okay, I'm going here versus here to figure out angles and vectors. Not that right-hand rule. Different right-hand rule. Okay. Textbook. All right, I am trying to get the history of this file. Sorry. Commits. I want to just change. There we go. Have all the textbook sections. So the right-hand rule is very, very straightforward and simple. And I'll open this up so that I have this view file. Come on. And then download raw file. Right-hand rule, very simple. The idea here is that the maze entrance and exit are always going to be on the same wall. So what you do is you place your hand against the wall and you just don't let go. That's it. Basically, you'll wander throughout the maze and it'll take a while, but you'll eventually get to where you're going. It's a very kind of simple strategy to get to the end of a maze. It's not a particularly glamorous one. It also works for the left hand. It works unless, of course, like the exit you're looking for is like an elevator in the middle and not connected. So in those cases, you need something a bit more powerful, which is depth first search. Which brings us to Greek mythology, of all places. Okay? So, let's see. Where is my picture of... Oh, I don't have my picture of the labyrinth. I thought I did here. So there is a thing in there's a myth in Greek mythology about a maze called the labyrinth, and unfortunately it does not star David Bowie. It is actually not that kind of labyrinth, unfortunately. Labyrinth, synonymous with maze, it is this thing from this kind of classical maze in ancient Greece. It is the labyrinth built by Daedalus for King Minos. So King Minos was a bit of a jerk, and he offended Zeus. And as Greek gods do, they caused it so that that Minos' wife gave birth to a half man, half bull somehow, called the Minotaur. And the Minotaur was basically tossed into this labyrinth that was created by Daedalus. And because, again, I did mention that Minos was a bit of a jerk, Okay, I do want to emphasize he was a jerk. He would just round up random Athenians and just toss them into Labyrinth to feed to the Minotaur. And he did this every so often until a demigod of who was the child of Poseidon decided to put a stop to this. This is Theseus, who was also a bit of a jerk. But he had the help of Ariadne, Minos' daughter, and with her help, he was able to navigate the labyrinth. And so here's the classical drawing that's labeled Theseus, Minotaur, and Labyrinth. And we can see here that he has his sword for Minotaur slaying. He also has in his hand, in super high resolution, Ariadne's thread, which is basically the thing you need when you're in mazes. You need some way to mark where you've been. See that thread marking where he's been? So Theseus slew the Minotaur, and then Minos escaped, and he died sometime later. And I want to make sure I get this exactly right. He died in a bizarre series of events involving him being a stalker, a seashell, and more thread. Because Greek mythology is wild. Wild. Seriously, it's great. Anyway, so the idea here is, since we're pretending we're a demigod protagonist of Greek myth, we might as well pretend that Ariadne's thread is magic too. It won't run out of thread. It's not going to get tangled. And so what we're going to do is that we will let the thread unroll as we are going through the maze. If we hit a dead end, if we come to a crossroads or some other choice, we will just travel down an unexplored passage. Eventually, we're either going to hit a dead end one of two ways. We either loop back around and hit where some of our thread that we've seen earlier. Again, thread is magic. Nobody's going to mess with it. So in that case, we need to backtrack. Otherwise, we hit a literal dead end. There's like nowhere else to go. Again, we need to roll back up and backtrack. So what we need to do is that we follow the thread back, roll back up, and then we have to mark the floor or the walls with our sword at that point. Like to kind of like say, hey, don't travel down this path. You've already come down this path. Make sense? So basically, we have three types of squares. Unexplored, we haven't this is the part of the maze we haven't gone down yet. Visited, which we have traversed, and backtracked, which means we've been here twice, the second time being us reversing our trail. And so we'll use a stack instead of a magic thread, and what we do is we push to a location to say that we're traveling to this location. So when you move by pushing on top of the stack, and then the top of the stack is where you currently are. If you need to backtrack, you pop, removing the top of the stack, right? And then what you can do to keep track of where you've been, rather than using a sword to backtrack, what you'll do is you use color. So our algorithm is as follows. While the maze exploration is not done and the stack isn't empty, we peek at the stack to get our current position. And then we check every direction. If we can go north, and we haven't visited there yet. If we can go north, the way we can check if we can go north or south or east or west is just by looking to see if there's a wall in our current cell. If there's a north wall in our current cell, we can't go north. Make sense? So we just simply check for all cardinal directions. If we can go in any of the cardinal directions, we are going to push that location onto our stack to go there, and then mark where we currently are some way as visited, again by coloring it or whatnot. If we can't go anywhere, we're at a dead end, right? So it's an if, else if, else if, else if, else statement. Mark the current location as dead end, and otherwise pop off the stack. Sorry, not otherwise, and then pop off the stack. All right? Now, also I want to just kind of just mention one bit of ease of thing that I did for you guys. okay, which is, if we go over here and generate our maze, you see how we've got our border over here? It's a bit hard to see, but there's a wall over here on the top and on this side as well. So that way you don't have to worry. This entire window is bordered, so you don't have to worry about going out of bounds if you check if there's a wall first, right? So it's time to answer a question you didn't know you had, right? So I'm not going to record. So actually, I'll record this bit. So like basically if, so I'll just use pseudocode. If there's not a north wall and let's see, and not visited, so if I is my current location, if row column is my current location, what is the north one, the square to the north of me? If I'm at row column, what is the square directly to the north of me? Is it? Row minus 1. It is row minus 1 because it's a matrix, remember? It's a matrix, so row minus 1. So remember, kind of XY is reversed from row column, and also for a lot of different reasons. One, because we're working with matrices, essentially, when working with 2D arrays. And two, when we talk about graphic coordinates, this top left corner is 0, 0, and we're working, and y going down is positive, so we're working in that bottom right corner of the 2D plane. So because of that, minusing your y direction brings you up. So anyway, now not visited row minus 1. If we are at index 0, okay? If we're at index 0 and I were to pass -1 into here, this would crash, right? Give me an index out of bounds error. But that's not going to happen because we check if there's not a wall first, right? If there's not a north wall, well, if there is a north wall, I'm not going to go. I'm not going to check that. Because, and we know that our top row has a north wall, right? I mentioned that our top wall has a north row. Row 0 has a north wall. So what's going on here is a bit of clever programming called short circuiting, right? And the idea here is that we've got an AND statement here. If we have an AND statement and the left side is false, we know we don't have to check the right side of an AND statement. Why? Because it doesn't matter what's going to go on here. It's not going to change the outcome. So why bother running this bit of code? That's inefficient. Make sense? Right? We're not going to waste computation power. But some programmers are idiots, and they'll put something like this here. Like they'll do an operation on the left side, on the right side of an and they'll wonder why it doesn't get incremented during this operation. It's because this code never runs. You shouldn't do that. You shouldn't run code like that in if statements. If you're going to make adjustments like that, do them atomically. Otherwise, you're going to be running into issues. Now, the solution to that, though, if you really want to be an idiot, is you can disable short circuiting. Okay, you can disable short circuiting. And so to answer the question you didn't know you had, the way we disable short circuiting is this. You use one AND. And that is why we use two ANDs and two ORs. Two ANDs works the logically and computationally efficient way to do things. So when we have an OR statement, if this side is true, it's not going to bother checking this side because that's computationally inefficient. it doesn't matter what this outcome's going to be. It's going to run anyway. So that's why we use two bars and two things for an and. So, and that's also why I suggested you want to switch this to check if there's a north wall first, rather than checking if the index is at the above. Because if you check if there's a north wall first, you don't have to check if you visited the if you check if you visited first, then before doing that check, you'd have to check if you were out of bounds, which is yet another check. So because we're checking if there's a north wall first, you don't have to check if you're out of bounds. So doing and statements and taking advantage of short circuiting can really help you. So just follow the pseudocode I gave you and it will look nice and efficient. All right, I was going to talk a bit more about maze generation, but I've already wasted half an hour of time here. So if you're interested, and I'll just simply say, if you're interested in learning how mazes are generated, which is the extra credit, right? Maze generation algorithm. Boop, 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 boop. Fun thing you can always do on these Wikipedia algorithm pages is go down to the below to the C also go down below C references, and then check out the external links because sometimes they're really nifty. It's like think this you can so you know this page is legit because it passes what we call the Taft test, which is that it is the Taft test. Does your page improve design when you replace every image with William Howard Taft? Basically, the idea here is that everything is too big, and basically, if we replace images of the basically we replace all images with the best with images of the best U.S. president by weight, then it passes the Taft test. So if it still looks good. So this basically you can tell it's legit because it's got old HTML styles and is very basic and talks about this stuff. This other one though about which is an HTML presentation with maze generation algorithms, just a very good slideshow on how to do mazes and the different strategies for building mazes, and it's really cool, and it's got runnable code in it, which is really cool. So yeah, all sorts of things here. Implementation of the DFS maze generation code in multiple languages, that Rosetta code, all sorts of really interesting stuff here. So anyway, with that, I think I'm done, and I'm going to go ahead and help everybody. Sorry for rambling on for so long. It's been a very interesting morning.